Hi, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into CAP theorem and consistency models, what I actually use in my Next.js e-commerce platform. There's a question I had to answer when I built my checkout flow. What happens when two customers both try to use the last redemption of a limited coupon at the exact same moment? Or when a Stripe webhook confirming a payment arrives while the user is simultaneously clicking to cancel? These are not edge cases. They are the moment when your database's consistency guarantees either protect you or produce a bug that's almost impossible to unwind. If I issue 2 licenses for one purchase because 2 concurrent checkouts both pass the is stock available check, I have 2 options. Revoke license that's already been activated and delivered, which is a customer service disaster and potentially a contract breach, or accept the financial loss and honor both. Neither is recoverable without cost. That's what makes consistency failures categorically different from most bugs. The CAP theorem gets cited in every system design interview, but most explanations stop at the diagram. This video is about how I actually use consistency guarantees on my own platform. CAP in 60 seconds and why PACELC matters more. Okay, the CAP theorem says a distributed data store can only guarantee 2 of 3 properties: consistency, availability, or partition tolerance. Consistency means every read sees the most recent write. Availability means every request to a non-failing node gets a response. Partition tolerance means the system keeps working even when the network drops messages between nodes. The key insight: partition tolerance is not optional. Networks fail. The real choice is CP or AP. During a partition, do you return an error to preserve consistency or return potentially stale data to preserve availability? But here's a more practical framing that CAP doesn't capture. CAP only applies during network partitions, which are relatively rare. The trade-off you encounter daily is between latency and consistency, even on a healthy network. Or this is what the PACELC model describes: partition, CP or AP, else, latency or consistency. Even without a partition, you can have low latency reads by allowing slight staleness or strongly consistent reads at higher latency. That everyday latency versus consistency trade-off is what most of my decisions are actually about, not the partition failure scenario. The consistency spectrum runs from strongest to weakness. Understanding the mechanism behind each level is what makes it a design tool rather than a ranking to memorize. Linearizability: the strongest means every operation appears to take effect at a single point at time between its invocation and completion, and all participants see operations in the same global order. No ambiguity about which write happened first. That is what Postgres' primary gives me. Sequential consistency relaxes the timing requirement but preserves order. All participants see operations in the same order, but that order does not have to match real-world time. Casual consistency preserves only casually related ordering. If A calls B, everyone sees A before B. Unrelated operations can be seen in different orders by different participants. Read your write guarantees that after your write, your subsequent reads reflect that write, but other users might still see older data. Eventual consistency, the weakest, guarantees only that if writes stop, all replicas will eventually converge. There's no timing guarantee, no ordering guarantee, just eventual agreement. Each level is a trade-off between how much you ask your infrastructure to coordinate and how fast reads and writes can be. Acid C versus Cap C. They're orthogonal. The C in acid is not the same as the C in Cap. They're orthogonal properties that are frequently confused, and conflating them leads to wrong architectural decisions. Acid consistency means a transaction moves the database from one valid state to another, satisfying all constraints. If I have Total sense is greater than or equal to 0. ACID ensures no transaction ever violates it. This is a property about the relationship between the data and the rules. Cap consistency means linearizability. Every read sees the most recent write across all nodes in a distributed system. This is a property about the relationship between nodes. A single node Postgres is fully ACID. It makes no cap claims because it isn't distributed. There are no nodes to coordinate. On my platform today, everything is ACID because everything hits a single Supabase instance. Here's the inflection point worth naming. When Supabase reads replicas are added to a deployment, cap decisions become real for the first time. A read routed to a replica might not reflect a write that landed on the primary 200 milliseconds ago. The ACID guarantees of the primary remain intact, but replica reads are eventually consistent unless you explicitly route to the primary. The transition from single node ACID is enough to replicas in play. Cap choices matter is an architectural boundary, and knowing it's coming lets you design for it before you hit it. Write skew. The isolation anomaly that matters. The isolation anomaly that matters most in e-commerce is write skew. Two support agents both process a refund for the same order. Agent A reads order status completed. Agent B reads it's also completed. Both check, can this be refunded? Yes. Agent A inserts a refund row. Agent B inserts a refund row. The order is refunded twice. Each transaction was individually valid. Read committed allowed both to read the same snapshot. Repeatable read doesn't help. Both transactions started before either committed, so both see the original completed status under repeatable read, just as they would under read committed. Only serializable catches this. But serializable comes from a mandatory design requirement. Your application must handle error, could not serialize across due to concurrent update, and retry the transaction. Code that uses serializable and does not implement retry logic will fail non-deterministically under concurrent load. The retry is not optional defensive programming. It's a required component. The structural fix is better. A unique constraint on order ID refund type makes the second insert fail regardless of isolation level. Select for update on the order row. Make the invariant enforceable at the schema level. An isolation level becomes a secondary defense rather than the primary one. My consistency map. Here's where theory meets actual platform. Orders and payments. Serializable with retry or select for update. Two concurrent webhooks cannot both transition the same order. The database guarantees this. Coupon usage. Select for update. My increment coupon usage if valid function locks the coupon row. First checkout locks, checks, increments, commits. Second blocks, reads 100, fails correctly. Order status after purchase. Read your rights. The confirmation page reads from the primary. The user who just bought sees their order immediately. Product catalog. Eventual consistency with ISR. 5-minute revalidation window. The checkout price is always read fresh from the database. The ISR, display price, and the authoritative checkout price are explicitly separate. Shopping carts. Read committed on the primary with optimistic updates. When a user adds an item, the UI updates immediately before the server confirms. If the server rejects, the UI must roll back. Silent rollback failures. This is where the server rejects, but the UI doesn't reflect it. This means the user thinks their cart has an item, but it doesn't. And search is immediately consistent. The TS vector column updates in the same transaction as the content. No asynchronous pipeline. A product published but not yet indexed is invisible to buyers. A potential lost sale. Audit logs. Same transaction as the primary operation. Always consistent. Always durable. Coupon exhaustion. My real double spend. A coupon with 100 allowed uses. 2 checkouts simultaneously read usage count at 99. Both check. The count is less than 100. Both pass. Both increment. That's 101 uses. So why doesn't repeatable read prevent this? because both transactions start before either commits. Repeatable read prevents a transaction from seeing changes committed after it started, but both transactions start at the same moment before either has written anything. Both see a usage count at 99 under a repeatable read, exactly as they would under read committed. Serializable tracks the dependency between the read and the usage count and the subsequent writes. It detects that two transactions with the same read-write pattern will produce a conflicting combined result and aborts one. But that means handing a serialization failure and retrying. My practical solution is select for update, lock the coupon row, first checkout acquires the lock, reads 99, passes the guard, increments to 100, commits. The second blocks, acquires after commits, reads 100, fails the guard. No serialization failure to retry, no 101st use. For license generation, a unique constraint on the order ID and license type makes the second insert fail with a constraint violation. The check then act race is eliminated structure. Session consistency. Read your rights. There's a consistency problem that isn't about concurrency. It's about user experience and financial consequence. A customer buys a software license. The write lands on the primary. A millisecond later, they navigate to their account page to download it. If that read is routed to a replica 500 milliseconds behind, the customer sees no license. They think that the purchase failed. They open a support ticket. Some initiate a chargeback. Some purchase again and create a duplicate order you would have to refund. The financial and support cost of a violated read your write guarantee is measurable. My strategy. For 5 seconds after any write, the subsequent reads from the same session go to the primary. Store the last write timestamp in the session. On each read, check whether 5 seconds have elapsed. If not, route to primary. If yes, replica is fine. The architecturally correct implementation uses the write-ahead log sequence number, tracks the LSN of the last write, and route to a replica only when it reports it has replicated up to that LSN. This guarantees that replica has your write, not just that some time has passed. When Supabase exposes LSN-based routing, that's the write upgrade. Eventual consistency. Not everything needs immediate consistency. The question is whether brief staleness causes financial harm, a security vulnerability, or a broken user experience. Product catalog, 5-minute ISR cache. The description changes take a few minutes to propagate. The user isn't making a financial decision based on a 4-minute old description. The checkout price is always read from the database, not the cache page. Search. It is immediately consistent by architectural choice. My TS vector column updates in the same transaction as the content. If I had used an external search service, a newly published product would be invisible to search for however long the indexing takes. Seconds to minutes. For an e-commerce platform, that indexing window represents potential lost sales. Postgres built-in search keeps that window at 0. For now, hopefully. The shopping cart. Read committed with optimistic updates. The optimistic update is fast. The rejection handler is what makes it correct. Silent rollback failure. Okay? Where the server rejects but the UI doesn't reflect it. This means the user thinks their cart has an item when it doesn't and discovers the discrepancy at checkout. Audit logs. Same transaction as the primary option. They're always consistent, always durable, never cache, never asynchronous. The consistency bugs I test for. Consistency bugs only appear under concurrent load. Sequential tests always pass. Read, modify, write. 2 transactions read the same value, modify independently, write back. One write overwrites the other. The fix for this is atomic update with a where clause or select for update. The test is fire 2 concurrent updates and assert the final value reflects exactly 1 increment. And for write skew, 2 transactions read a shared condition and write to a different row. The combined results violates an invariant. The fix for this is serializable or select for update on a shared row. You test this by having 2 concurrent refund attempts on the same order. Assert exactly one succeeds. Phantom reads. A transaction re-executes to range query and finds rows that didn't exist at the start. The fix. Serializable or explicit range locks. The test. Have concurrent insert and count. Assert the count reflects the pre-insert state within the transaction. For concurrent tests, a promise that fires both operations simultaneously. For more reliable saturation, K6 can fire hundreds of concurrent requests against a specific endpoint, reliably triggering race conditions that promise that all might miss. Run these against the real Supabase database, not mock. Bringing it all together, right? Choose the weakest consistency you can actually afford. Cap forces a choice during partitions. PACELC is the daily trade-off. Latency versus consistency on a healthy network. Most of your decisions are PACELC, not cap. Acid C is not the same as cap C. Single node Postgres, acid yes, cap not applicable. Replicas make cap choices real for the first time. Orders and payment transitions. Serializable with retry or select for update. Two concurrent webhooks must not both succeed. The product catalog. Eventual consistency via ISR. Display price is informational. Checkout price always reads from the database. They can differ by 5 minutes. Read your rights after purchase. It routes to primary for 5 seconds. A stale read after buying a license produces support tickets, chargebacks, and duplicate orders. On Fleshed Out Thoughts, I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're thinking through consistency guarantees for your own platform, isolation levels, select for update patterns, read your rights routing, reach out. I'm open to freelance projects and consulting. The full post is linked in the description, complete consistency map, isolation level decision guide, and the test suite for concurrent operations. The next in this series is rate limiting, how I protect my checkout and login endpoints from abuse, and the path from in-memory map to distributed Redis enforcement as scale permits. I'll see you there.